we've seen the concept that moments of inertia of an object, moments of inertia of individual masses on an object can be added. What do we do about something like this rod? Consider this to be a rod, a uniform rod of length L, mass M, fixed to rotate about an axis of rotation that goes into the board here, or comes out of the board, doesn't matter. And we don't have individual masses here. We have continuous mass distributed from one end to the other. That's what we mean by a uniform rod. Continuous mass distributed from one end to the other so that any given length of a part of this rod has the same mass as the same length of another part. Okay, so the uniform rod. Now my question, okay, well what we want to do is we want to think this thing obviously has a moment of inertia. If we get it spinning around this axis, it's going to have a kinetic energy, and that kinetic energy should be equal to 1/2 I omega squared. Just notice that the camera isn't picking up my labeling of the length L here. Okay, so we want to start to get a handle on that, and what we're going to do is we're first going to consider what's the mass and then the moment of inertia of an increment of length delta x. So in the first place, the moment of inertia depends on where that increment is, but the mass doesn't. So anywhere on this rod we have a length delta x. So let's just say right here we have some small length delta x on this rod. So I want you to take a minute and pause and tell me what the mass of that small length unit ought to be, delta x, in terms of m and L. Okay, well, you should have done that. I'm going to do it for you now. There are a couple of ways we can do this. We can say, well, the mass is in the same proportion to the length delta x as the mass of the big rod is to the length L. So if we let delta m stand for the mass in that small increment, it's going to be delta x times m over L. Think about how I wanted to arrange that. Now there's another comment I can make. We'd actually be better off thinking of a mass density, which is m over L. That's the mass per unit length, and multiplying it by the length. So another way to see this is the mass density, I should say a linear mass density, is m over L, and the mass density times a length equals the mass in that length. And by a length here, I don't mean the total length of the rod, I mean any length within the rod. And that should be a fairly straightforward idea for you to grasp. So the idea of mass density, and that's the way things are usually done. When we have a constant mass density, we can do this. Since the rod is uniform, we have a constant mass density, we can go to the proportion. In general, as you would know from first year calculus, the typical application problems, you can have a mass density function. So this might get denser. It might actually get a little wider as you go out. So it might get denser as you move away, or less dense. Okay. Now, the next question is, what's the moment of inertia of this mass if it lies at distance? Now I got delta x there. I don't know what I'm writing sometimes. I'm going to call it x star from the axis. What would be your expression for the moment of inertia? You should pause and write that down. Stay active. Don't view this passively. Okay, well, the moment of inertia would be and I'll call it delta I, the contribution corresponding to the length delta x, just as I use delta m here, which is a contribution to the mass of the length delta x. Delta I is going to equal what? It's going to equal, well, it's mr squared, where r is the distance from the axis of rotation, but r in this case is your x star. So that's delta m times x star, just about star that x, squared. So there's the moment of inertia. Now, what we're going to do is we're going to, I'll ask you to write the expression, but I'm going to pause this and write it off screen to save a little time here, to save you a little time. Okay. Now, I said delta I equals this. I should say delta I approximately equals this, because we don't know where this, we don't have just one distance that characterizes how far this is from the axis. So when I put x star, I say it's a distance x star. We don't really know what x star should be to measure this moment of inertia, but if it's a small moment, any x star that falls within this interval will give us a pretty good approximation. And you should be used to this from calculus. You should have actually done moment of inertia calculations in your calculus class under the applications. Any calculus class prerequisite to this course, I would think, would cover this sort of thing. But so this should be sort of a refresher, but you might have used a different notation and so forth. The idea is, of course, that we subdivide this entire length into small increments. There's a sample point within each increment that's a distance xi star from the moment of inertia, or from the axis of rotation. And the typical increment, the increments are numbered. We have a delta x1 first interval, a delta xn last interval. Those notations are pretty standard. And for each interval, we have a sample point x star. And for the ith interval, so here's the first interval, here's the last, the nth interval. The ith interval has a width delta xi, a sample point at distance xi star from the axis of rotation. Okay, I'll abbreviate of rotation there. So my question is, what's the expression for the total moment of inertia of this rod? You should write that down as best you can. I'm going to continue then. So I'm going to actually write this one out in front of you because you need to see it. I assume that you might need to see it. I don't know that everybody does, but let's see what we get. The moment of inertia would be the sum, and it'd be approximately equal to, because we can't write the exact moment of inertia. We don't know where any of these xi's is within its interval. But the moment of inertia is going to be the sum from I equals 1 to n of what? Of the mass. So that's going to be delta m sub I multiplied by xi star squared. So that's one expression, but it doesn't give us all the information that we assume here. It doesn't use all the information we assume that we have. So the sum from I equals 1, what's your delta m sub I? Well, your delta m is delta x times m over L. So we have delta xi times m over L times xi star quantity squared. Now you probably suspect it, you probably know it darn well. We're leading up to an integral here. Okay, so let's see, m over L is constant. Shouldn't have written my equal sign so readily. So we're going to have m over L times the sum. We can factor out the m over L from every term of xi star squared times delta x sub I. Now, at this point, you should see that this is going to approach the integral of x squared dx times m over L. Maybe I can readapt. Nah. Just let it be messy. This approaches m over L times the integral of x squared dx, which is m over L times x cubed over 3. And of course that integral goes from one end of the object, the rod, to the other, so that integral goes from 0 to L. And I'm sorry, I crowded that a little bit, bad planning once more. So this is evaluated between L and 0. So what you get is m over L multiplied by L cubed over 3, which is 1/3 m L cubed. Okay, now you can look in your book for the formula of the moment of inertia of a rod of length L and mass m, and that's exactly the formula you'll get, provided the rod is rotated about its center. So this is how we calculate moments of inertia. We consider the contribution of a small portion of whatever object it is, and then we expand that into a sum that represents the moment total of all the moments of inertia of the small parts, and we let that sum approach an integral in the way that we should have seen in our calculus courses. I'll say that this is a little bit of a stretch for most calculus students. I know when I came out of first year calculus, it took me about my sophomore year before I completely really mastered all this stuff. I was doing that in the context of electromagnetism by that time, but it can be a challenge. So you want to review your calculus. You want to think about what's going on with this process.